In this video, we're going to do several applications of exponential growth. So in the example one, we're going to use the population growth model, n of t equals n naught times e to the rt. So we've got a population of a certain species of fish. The growth rate is 1.5% per year, and the population in 2010 is 10 million. Okay, so part A, we're supposed to find an exponential model for the population where t equals years past 2010. Okay, so if 2010 is our beginning time, t equals 0 is 2010, so then n naught would be that 10 million. That's the population that we had at the beginning. Okay, so that's n naught is 10 million, and then our rate in these problems, we're going to write 1.5% as a decimal, so 0.015. So putting that together, that would give us that our equation is going to be n of t equals n naught is 10 million times e to the 0.015 times t. There's our model. In part B, we want to know the population of fish in 2015. So in 2010, that would be a t of 5. So we're going to put 5 in for t. So it would be 10 million times e to the 0.015 times 5. And that is approximately 778,842 fish. And part C, how long will it take the fish population to double? All right, well, the initial population is 10 million, so doubling it would be 2 times that. So 2 times 10 million, that's going to be our output, and we want to know the time needed to get to that output. So we're going to have 10 million times e to the 0.1 or 0.15 t, and we need to solve for t. The first thing I'm going to do is divide by 10 million. And that would give me that 2 is equal to e to the 0.015 t. And now I'm going to take the ln of both sides. 0.15 t. And now if I have an exponent up inside a logarithm, that gets to come down and become a coefficient. So then that can be written as 0.15 t times ln of e. But ln of e, what does that mean? That means log base e of e. E to what power is equal to e? That's just 1. Okay, so then that would give us that the ln of 2 is equal to 0.15 t, and dividing both sides by 0. Oh, I forgot a 0. 0, 1, 0, 0.15. So the t is approximately 46.2 years to double. All right, let's try another one. Some bullfrogs were introduced to a small pond. The graph shows the bullfrog population over the next few years. Assume the population grows exponentially. So what was the initial population? That would be the y-intercept. Okay, so that is our y-intercept. So that is, so let's see, we're going to use the formula n of t equals n naught times e to the rt. So n naught is equal to 100 frogs. Okay, next part, find a function that models the number of bullfrogs. So the population is given by 100 times e to the rt. Well, we don't know what the rate is. So what we're going to need to use is we're going to use this point to find our R. All right, so at the output is 225 when the input is t, so e to the r times t of 2. And then we can divide both sides by 100. And then we can take the ln of both sides. So let's see, 225 divided by 100 would be 2.25. Taking the natural log of the right side would give us natural log of e to the, I'll just write that as 2r. Okay, and now we have an exponent inside an argument, so that gets to come out and be written as the coefficient. ln of e, that's just worth 1. Okay, so then we would get that 2r is equal to ln of 2.25 divided by 2. So r is approximately 0.405. And now part C, we need to know what the projected bullfrog population will be in 10 years. So let's see, in 10 years, we're going to have that initial population of 100 times e to the r. We just found that 0.405 times number of years is 10. And that gives us approximately 5,739.7. So that's approximately 5,740 frogs. All right, so we found that the bullfrog population is growing exponentially with a rate of 0.405, so that would represent 40.5%. And so that tells us that in 10 years, the projected bullfrog population will be 5,740 frogs. All right, now let's look at what happens with radioactive decay. So this is this can model how radioactive substances decrease over time. It also is how medication decreases in our body over time, things like that. So let's say that we have 250 milligrams of a radioactive element, and it decays to 220 milligrams in 24 hours. Find the half-life. So we want to find this half-life right here. All right, using this formula, if I multiplied both sides by h, and then I would get r times h is equal to ln of 2, and if I divide both sides by r, the half-life is ln of 2 divided by the rate. So if I could figure out the rate, then I'd be able to find my half-life. So we can use this formula for radioactive decay, where m naught is our initial value. So let's see, if I take m naught in this case was 250, okay, and then in 24 hours, the output is 220 milligrams. So we'll use our formula. Oops, 24 is equal to the initial value, so 250 times e to the negative r times t, and in this case we're going to use 24, and we know that that gives us 220 as our output. Negative 24 times r. Good, so I'm going to divide both sides by 250, and so then that would give me, let's see, 0.88 is equal to e to the negative 24r, and then we can take natural log of both sides, e to the negative 24r, and I have an exponent inside an argument, so that's going to come out and become my coefficient. And then remember, ln of e is 1, so we've got the ln of 0.88 is equal to negative 24r. And dividing both sides by negative 24, we get r is equal to ln of 0.88 divided by negative 24, which is approximately 0.005326. All right, but I'm not done because I still needed my half-life. Okay, so let's find half-life. Okay, I'm going to use the half-life is equal to ln 2 divided by r. So we would get ln of 2 divided by 0.005326. And that is approximately 130 hours. All right, let's try another one. So in this example, after 4 days, I have a sample of radon 222, and it has decayed 62% of its original amount. We want to find the half-life and then use that to figure out how long it will take for the sample to decay to 20% of its original amount. Okay, so let's think about this. It has decayed to 62% of its original amount. So I'm going to just let my new amount, that's going to be equal to 62% of the original. Well, I don't need to let that, that's given. Okay. Now, my original is what we're calling m naught in our equation. So we've got m of t equals m naught times e to the negative rt. So that's our model of decay. All right, so we have our new amount, which is m of t, and that's going to be 62% of the original. Okay, and we're using our formula negative rt. All right, so we've got 0.62 of the original, which is m naught, and that's equal to the original times e to the negative rt, which is 4 days. Okay, so let's divide through by m naught. That gives us 0.62 is equal to e to the negative 4r, and then we'll take ln of both sides. And if we have an exponent inside an argument, it gets to come out and become the coefficient, so negative 4r times ln of e, but that is just 1. And then we can divide through by negative, let's see, I was thinking negative 4 and I wrote it down. So let's see, so ln of 0.62 divided by negative 4 is our r. And then that is approximately 0.1195. So that's our rate. And that was what we were asked for in part A. All right, and now we can write our model. So m of t is equal to m naught, which times e to the negative r, which is, so it would be negative 0.1195 times t. Okay, and in part B, we want to know how long will it take for the sample to decay to 20% of its original. So 20%, we'll write 20% as a decimal, so 0.2 of the original, which is m naught. And then that would be times e to the negative 0.1195 t. And you can see here that when we just divide through, that basically that decimal, we're going to take the natural log of 0.2. And that's going to be equal to natural log of e to the negative 0.1195 t. But remember, if you have an exponent inside the argument, it's going to come out and be our coefficient times ln of e, but that's just 1. Okay, so basically what happens here is you get to take ln of that percentage, but just write that as a decimal, and then that would be equal to the rate times time. 0.1195 times t, so t is ln of 0.2 divided by negative 0.1195. All right, approximately 14 days. Okay, so let's just double check. I found how long. Here, though, I found the rate, but I'm not done because I actually need to find the half-life. Okay, so let's keep going on that one. So half-life is, let's look again how we had it, ln of 2 divided by rate. Ln of 2 divided by our rate, 0.1195, which is 5.8, so that's about 6 days. Another application that uses exponential growth is Newton's law of cooling, and this is extremely helpful because we can figure out the time of death based on the surrounding temperature and the temperature of the body when it's found. So here's how this works. The D naught is the difference between the initial temperature and the object. So a normal body temperature is 98.6. So in this case, D naught would be the difference between normal temperature and the temperature when it's found, which was 60 degrees. So that is 38.6 degrees. All right, K for, it just depends, but for for human bodies is 0.1947, and T is in hours. And the surrounding temperature was that 60 degrees. So that is 60 degrees. So we're going to put that together and we can come up with a model. So the temperature with a time of t is given by the temperature of the surrounding area, which is 60 degrees, plus the difference between the temperatures, so that's 38.6, times e to the negative k, and we're going to use k of 0.1947 times t. So there's our model. Now we can solve this. If the temperature of the body is 70 degrees, how long has the person been dead? So we're going to find t, little t. Okay, the temperature is 70 degrees. And e to the negative 0.1947 t. We need to solve this for t. So we're going to isolate that exponential term. We'll subtract 60 from both sides. 0.1947 t. So that gives us 10 is equal to 38.6 times e to the negative 0.1947 t. And then we can divide both sides by 38.6. 38.6. And so that gives us that 10 over 38.6 is equal to e to the negative 0.1947 t. Taking the natural log of both sides, 8.6, right, we would have ln of e to the negative 0.1947 t, but that gets to come because it's an exponent in the argument, that gets to come and be the coefficient times ln of e, but ln of e is 1. Okay, so now we're just going to divide both sides by negative 0.1947 to solve for t. So t is approximately 6.9, and we're measuring this in hours. All right, so we can just check our watch and figure out time of death.